Please welcome. Over here.
Thank you, Nick. I think one of my duties here is on the last one to say, woo, thank you, organizers. It's pretty awesome. So first I'll do a little give and take. So with a little give and take, you can give me a smooth, simply connected format. So you can keep it in your mind or shout it out. And then for this trick, after you have a smooth, simply connected four-manifold, I add on a bunch of copies of S2 times S2 and hand it back. And then you pick any embedding of a surface, an orientable closed surface, into this four-manifold. It can have any genus, it can have any self-intersection you like. It needs to be homologically non-trivial. That's the only key thing. Fundamental of its exterior could be unknown to be extremely good. It doesn't have a whole lot of restriction, though. It's just homologically non-trivial. And then from that, I will generate an infinite collection of smoothly embedded surfaces, of smooth embeddings that are all topologically isotopic. And we'll know that even though we won't know what fundamentally the exterior is. They will be smoothly distinct, and they will remain smoothly distinct. So given any genus, I can do that number of internal stabilizations, meaning I can go in a distributed coordinate chart of that large genus, and there'll be a pair of these that are still distinct. So the internal stabilization diameter of this set of surfaces is infinite. In fact, you can prove much more. A little bit, stating what it is that will prove much more will give you a hint about how part of the proof is going to go. Maybe I should pick up a pen and wobble across the room. Maybe I'll pick up a different pen. So let me start out with a definition. And so this will be subtly, time. And so we'll take two embeddings, J and J prime, going from a surface and it'll be smooth embeddings into the four-manifold. And to be subtly knotted will mean that SK, if and only if, there exists a diffeomorphism. Here I'll say orientation preserving, just because it will allow me to do a comparison to the classical case, such that J prime will equal alpha composed J. So the very first comparison with classical knot theory, if you have a classical knot and even there's a homeomorphism that's orientation preserving that takes it to another knot, then there's a smooth isotopic aging the one to the other. That's going to be drastically false in four dimensions. Such that, so here are the three ways that these things are going to be the same that makes it sum. The first thing is alpha is going to be topologically isotopic to the identity map. And by the way, so that really says, hey, we're not doing something silly, just like creating a homology class for taking the exterior. One of the things that Annabelle has been looking at is when we look at embeddings, we want to say, hey, if the complements are distinct, then that's really sort of a cheat. In fact, in the classical case, if knots have the same complement, then they're the same. Here in the case of surfaces and four-manifolds, again, this is wildly different. There's a smooth diffeomorphism. It takes one knot to another. And so that makes complement one to the other, yet will still be distinct. Some people have been talking about comorbidism and concordance. These things are going to be smoothly concordant. Even more than that, this alpha is going to be C infinity pseudoisotopic to the identity. The third condition here on how they're the same is it really is a big difference between external stabilization and internal stabilization. This diffeomorphism, we can in fact make it to be the identity on a disk. That disk can be disjoint from the surface, and so that we can then make sense of taking a connected sum of this diffeomorphism with the identity on S2 times S2, and alpha plus the identity on S2 times S2 will be smoothly isotopic to the identity on X plus S2 times S2. And so even though they are the same in all of these ways, so they're topologically isotopic, ambiently, they are smoothly concordant, they become equivalent after one external stabilization. These things are still not smoothly isotopic. So J and J prime are not. The identity. So that's the main game, main feature we're talking about. And so to prove this works, let me actually give a theorem statement here. And so, and I'll give it in closed case if for surfaces without boundary. I'll remark that you can also prove things for four-manifolds with boundary and surfaces with boundary properly embedded, but you know, you don't want to listen to me jabber that way. So for any x4 closed, I1 equals 1, there exists an in such that if you let z equal x plus in copies of S2 times S2, maybe I'll make this plus 1 looking ahead. That then for any embedding J0 going from the surface, which is closed and oriented, into Z, there exists a family JP going from sigma into Z, such that the JPs and JQs are subtly knotted. This is P equals 0 to infinity. Subtly, smoothly knotted. And this is, I think, kind of big, interesting. And for any genus that you pick, if you take, there will exist a P that depends on the G, so that if you take JPG and you sum on just the standard embedding of the surface of genus G into the photosphere, and think of this going from sigma into, we can think of it as Z plus photosphere, which is just Z. And so I just, in the definition of the submanifold, yes, I found it. Let me start over. Sure. Subtly knotted means that they're related by a diffeomorphism. The diffeomorphism is topologically isotopic to the identity, smoothly pseudoisotopic to the identity, and becomes smoothly isotopic to the identity after you add one copy of S2 times S2, and yet you still can't smoothly deform one into the other. And the theorem statement, wow, that is horrible. Quickly. all X, Y, one closed. There exists in Z equals X plus one S2 times S2. That should be all J0 sigma closed orientable smooth to Z. There exists JP going sigma into Z infinity, smoothly knotted. And for all G, there exists a P of G such that J P of G plus the standard inclusion on surface of genus G in sigma plus sigma G into Z plus S4 equals Z. And J of 0 plus the standard inclusion sigma plus sigma G into there are smoothly knotted. Okay. Is that readable? We've got a theorem statement up here. So we'll prove this theorem today in short order and then go enjoy the beach. In fact, JP and JQ, unless you have the same things, they will be distinct. And so remain distinct, pairs of them after you add tons of trivial handles and trivial coordinates. Make sense what I'm trying to prove? So let's get started and prove it. So the first thing I have to deal with is how to construct the z's given the x. I'm just going to add on a lot of stuff. But in fact, this means that we really just have to prove it for a family of, the way you get exotic surfaces is you're going to start with exotic structures on manifolds that you know. And so I'll do a geography problem. I will do a geography in a slightly unconventional way. Instead of looking at it like C1 squared is a holomorphic Euler characteristic that seems to be the geographer's favorite math, I will look at the rank of the intersection pairing and see. And in here, we can build a line that is sigma equals 3/13 times the rank, and another line sigma equals negative 3/13 times the rank, and we can pick some constant over here, and then fill in this area of lattice points of rank and signature, and I claim that every allowable lattice point in here, everyone that's conceivably can be represented, is represented by a symplectic manifold of a given type, either spin or not spin. And so this is really a special case of for part mode 2, triple years off the age there. The basic construction here is you use iterated branch covers of CP2. You do double branch covers, you can get things like the elliptic surfaces and the Harakawa surfaces. You do an interesting one where you do a threefold. In fact, you can just do a little complication, basically. Riemann Gibbs compute the signature, of these algebraic varieties and the projectives of the symplectic. You can find chloride in them, and you can fiber sum them together, and you build this nice class of manifolds. The interesting thing for us that will help in this thing is not only are all of these things smooth, but so all allowable are represented by symplectic, and a symplectic that contains a symplectic embedding of the into nucleus. And by that, the into nucleus is a neighborhood of the sphere of self intersection -2. So we know what it means to be symplectically embedded there. And it has a torus as part of vibration, so it has self intersection 0. Called the sigma. And then this torus has a couple of so-called vanishing cycles that will draw in here like this. And this can all make sense in the symplectic world, and that will be useful. In fact, the main reason that this is useful is we know that Sider-Whitney variance for symplectic manifolds are non-trivial, and we can then do stuff. And so let's see. Of course, when I talk about allowable, we now know that the B plus is going to be odd. And if spin, the signature of, I'll call this Z prime X, is going to be congruent to 0 mod 16. Otherwise, we have no whole find. But as soon as you have those, you have it. So, just in case somebody says, hey, can you repeat that at the end of the talk? We'll manage. But at the same time, we will see the definitions. So you might not know if I proved it or not. So, these are topologically isotopic. They're smoothly concordant. They're one this time externally stably concordant, but they are not smoothly isotopic. They're not smoothly isotopic even after adding large numbers of trivial handles. Which a fun exercise to do is just even in the free sphere, if you take some knotted surface and add a bunch of handles to it, if you use those handles to unknot it, make surfaces filled. There's essentially a ton of stuff, some fun pictures for a general audience. Good. Good. There. All right, so where do we start? So here's the manifold X that you handed me. It has a given signature and rank. And we add S2 times S2, which is symmetric, and so it has 0 signature, but it has 2 homology classes, S2 times a point times S2, so now rank 2. That jumps it over, and then we just keep adding. And eventually we land at a point here. And this is why I want to do the +1. And so there exists an in such that if I gave X plus in plus 1 copies of S2 times S2, that is going to equal one of these manifolds that I'll call ZX prime plus S2 times S2. And in fact, at the same time, basically because I'm allowed freedom on how many of these things I add, if I change the orientation on X, I can use the same in. So I can take negative X and I can add in plus 1 copies of S2 times S2. And I'll end up at the manifold that I hit when I start from negative X, which switches the signature and hits in this point. And then I'll add on just one more S2 times S2. And so it's 1 is enough, quote the argument, to get to 1 as non-specific manifold plus 1 extra S2 times S2, which is part of the construction that follows from the word here. And so now we can break the thing into cases, or not really 8 cases. Proof. I think, so you don't fall asleep after lunch, it might be 1 and you still might fall asleep, but let's try to draw a 3 here. The first case is spin or not. start out here, and we'll spin or not spin. Then the next interesting case is we can take a look at the self-intersection of the surface that you get in homology, take it square. And this thing is either going to be bigger than or equal to 0, or it's going to be less. Then after you do that, yeah, I guess I just need one more. It's either going to be characteristic, meaning its complement is, well, meaning that it dot with any class is congruent to the square of that class mod 2, or it will be ordinary. And there's the same cases all the way down. I will show you the proof for this case. Okay. And so first we're just going to quote some old school results. And so, and by the way, I didn't say what Z is. This is D. Manifold that we get from this pattern after stabilizing one more time. So what do we need? Well, the first thing we need is a result from Wall, where he looked at the unimodular indefinite forms where the rank was, say, the rank minus the absolute value of the signature is bigger than or equal to 4, so that you have a little bit of wiggle room. And he classified elements up to automorphism. This is Wall's orthogonal automorphisms paper. And in particular, he shows that any two elements with the same divisibility, type, and square are related by an automorphism of the intersection theory. And then Wall's diffeomorphisms paper tells you that if you add on at least one extra S2 times S2, that gives you enough diffeomorphisms just inside that S2 times S2. And you can do linear algebra, so you can get all automorphisms. So these two results imply that there exists a diffeomorphism going from Z to itself, orientation preserving, so that when I take C compose J0 of sigma in the homology class, that this has a particular form. And in fact, I should name what the form is. So this T, I would call the homology class of the torus in the nucleus B1. Notice that its squared is 0. And I want to make something that looks like an S2 times S2. So I want something that square is 0 and get this once. If I take sigma plus T, well, when I square that, it's sigma squared, which is -2, plus T squared, which is 0, plus 2 times this times this, which with respect to 1 point, 2 and -2, even after lunch, is still 0. We'll call that one A1. And all of our homology classes up to a diffeomorphism are going to be 2 times the divisibility of the class times A. Well, the divisibility will be even for a characteristic element being an even. And then plus 2D pick up the divisibility of an extra K times a B1. Okay? So now I know at least the homology class of this element, and then I can go forward. Well, on the other side here, the way that we are doing this is we're not really constructing other surfaces, we're really constructing diffeomorphisms. To do all this, all we have to do is walk like an Egyptian in order to understand what a reflection in a sphere of self-intersection 2 is. The sphere of self-intersection 2 is just the 0 section in the tangent bundle to the 2 sphere. And in the tangent bundle to the 2 sphere, we have a map where, this is my sphere of radius 1 cubed about this center. I can multiply by -1. If I stick a tangent vector here, I can multiply by -1. And if I want to understand what's happening on the whole tangent space, it's useful to stick another vector here and recognize that even though this map is the antipodal map that acts as -1 on homology, that it's actually orientation preserving on the tangent bundle, and I can stick my thumb out to get a frame. In fact, I get a frame, which is an element of SO3, that gets mapped to this one, which is this goes to its negative, this goes to its negative, and this one goes to its positive. So we just have a 2 by 2 negative, negative, and a 1. We just do 180-degree rotation there. And so I do this Gibson map in around the 0 section, and then I do this isotopy going from a radius of 1/2 out to a radius of 1 in this bundle, and then I can catch that in anytime I see a sphere inside a four-manifold. We can also do the same thing if we have a sphere of self-intersection -2. And so this means that we're just looking for spheres, and we've luckily added on an extra S2 times S2, so we have spheres. And so I will call that Egyptian reflection R sub S, where this S is a sphere. Okay, so I guess I need a little bit more. The whole reason that I had these tori stuck in here was so that, well, you can do stuff to it, like surgery times a circle, better known as a log transform. And so, in fact, I will let this is not editorial comment. So you can have Zx prime semicolon 2p plus 1. And so this is the odd log transform. The odd log transform on an even manifold will be an even manifold. And this is log transform. And one of the things that you can do about this is we can arrange so that with the original one, the reason that we wanted it to be symplectic is so that we know that the canonical class of that thing was a basic class, which via the adjunction inequality, you can see that the canonical class evaluated on this class A1 and on class B1 will be 0. And then you can use late 90s gluing results of Morgan, Rothka, and Zalo that will tell you what the Seidler-Whitney variants of this thing are. And it will tell you in particular that if you compute the Seidler-Whitney variant of this in a class that is 2 times P times the class of the torus, which is B. Actually, many people quote Morgan, Rothka, Salo, Cows, but I haven't found a copy of that paper, which bugs me. And so it might be in Etherware. It actually is stated the way I want in the one by Morgan, Rothka, Salo. So it is published in that research letters, so you can find it complete. Modulo, the usual from the kind of various edge. Using Morgan and Rothka in the same way we get, quote, Tom's not here to in spirit. So this thing in absolute value is going to be here is going to be 1 is the relevant thing on these basic classes. The other relevant thing about this is that when we stabilize, so first, this doesn't change the fundamental group because, when you cut it out, you're not changing anything. It's a sectional theory. And it doesn't change the intersection theory. You need to think about what this long transform is a line that's odd. And so Friedman tells you that there is a homeomorphism, which I'll use a sharper letter, going from the weird guy into not weird guy. Just talking about weird. And then, and that can even be the identity on the disk. Then, if you look at Mandelbaum, Moizan, Gump flew in and his some elliptic surfaces, you see that if I add this to an extra copy of S2 times S2, that these will be diffeomorphic. In fact, since it has an extra S2 times S2, I can change the action on the automorphism group of the intersection pair to be anything I want. And so this being a smooth map, I'll use a smooth letter, is PP, and I can assume that PP is homotopic psi P plus the identity on S2 times S2. Yeah. So now that I got this and I have my reflections, I can construct my diffeomorphism. And somehow this result is much more satisfying than the exotic, weird, homotopic groups of embeddings that Danny and I have been thinking about because it's more concrete, surfaces, but we use some of the same idea. We're using some exotic diffeomorphisms, which it's really convenient to write these things as a commutator. So, you know what? Since this is the subtle part of the proof, I won't write it in a small word. I'll write it. I think. More erase me. So alpha P, I'll call it prime because I'm taking that data and put it in the standard form and kicking it out. We can just sort of conjugate by that if I want to get the exact alpha P's. This thing is just going to be the commutator of EP together with the reflection in A0. In the final S2 times S2, I call this sphere A0 sphere, call this one B0 sphere. And A0 plus B0, 0 plus 0 plus 2 times 1 is square 2. And then A0 minus B0, 0, 0 minus 2 is square negative 2. So those have our reflections. And let's just write out what this means. This means EP and then R, let's call this R plus, R minus, EP inverse. And then it'll be the inverse of this, which is going to be an R minus inverse, and R plus inverse. A little bit, if you look carefully, these aren't exactly the same R and R minus. It's not the same because we're going back and forth between the manifold where we log transform or not. Yes, we're adding on an S2 times S2. But, I mean the spheres and the corresponding pieces. We can actually do a little bit more to this, but make them the same. And that's because the psi plus the identity is the identity on the S2 times S2. So it doesn't change what the reflection in the S2 times S2 does. And so that means I can write this as psi P of EP plus compose psi P plus 1 SS. to the negative one of R plus, R minus, and psi plus one, no inverse, EP inverse, R minus to the negative one, R plus to the negative one. Again, I've slightly changed the R's, but it's not really changing the R's because I'm the identity on that factor of S2 times S2. Now we see the first bullet of my proof of the subtle part. It's me trying to be subtle. This thing is topologically isotopic to one. So is this. And once I isotope those to one, those things cancel out. And so this is the top iso. So the next thing that we need to do is get to the smoothly concordant or the pseudoisotopic. And if you think about it a little bit, doing a conjugation of a reflection in a sphere is the same as doing reflection in the image of sphere. So it means that I just need to insert in an EP inverse psi plus one, psi plus one, and EP. And when I look at this piece, this is just going to be R plus of phi psi plus one of A plus B. And then this piece will be the same thing with R and minus phi psi plus one A minus B. And then R minus negative one, R plus negative one. But now a groovy thing happens. This thing was homotopic to the identity. And so that tells you that this thing is the same homology class as this thing. And the complement of this thing, when I take an A and I add or subtract the B, there's another sphere that's geometric dual to this, so its complement is simply connected. So a result of Scaduto using old school topology shows you that this sphere is concordant to this sphere. Using the concordance between these spheres gives you a pseudoisotopy between these this diffeomorphism and this with the negative, so that cancels out. But then the same thing happens here, and so just by quoting Scaduto, this thing is pseudoisotopic to the identity. And then you've got one other thing. You want to look at one external stabilization, and in fact, this sphere and this sphere satisfy the hypothesis of the one is enough theorem that I call SCRIM. This was my work with Anna Schwartz, Stephen Kim, Danny Ruberman, Paul Feldman. Implies that if you take this here is going to be isotopic, smoothly isotopic, after you connect some with an S2 times S2, you just be A0 plus B0. And so that means this thing is, so this is part 3, that's same after one external. So the only thing that's left, now that I convince you that these are so much the same, hey, are they exactly the same, is I want to convince you that they're really distinct. And so something has to give. I'll be able to make this. And so, in fact, I'll prove that they're distinct after you add on enough copies of genus. And so this means I'll prove that question, why would the fact that JP is smoothly isotopic, JP plus standard embedding on the surface of genus G is isotopic to J0 plus the standard embedding on the surface of genus G imply that G is really, really big. Okay? So to do this, we're using parameterized stage theory, and in particular, parameterized cyclic width. One parameter. And so let me give some description. So in order to write down the cyclic width equations, you need a little bit of data. One bit of data that we need is we need a spin C. So there's actually some other data to get these equations. You need a metric, and you need a perturbation. And a typical model of perturbation is this is going to be a self-dual real tuple. And so from this, you can write down the Seiberg-Witten moduli space using this spin structure, using the data G and eta. And you might hope that the virtual dimension of this is equal to -1. In other words, the number you completely do the index formulas of dimension over minus the dimension of the kernel. If that's the case, and somewhere in the middle of this, if you have an alpha is a diffeomorphism from Z to Z, with orientation preserved, then I can pick a generic family of data so that if I look at G1 eta1, that is equal to alpha pullback of G0 eta. Then given that, you can take not just the moduli space for one particular method and perturbation, but you can take the union over all GT eta T. And since this has one X dimension, this is a zero-dimensional space, and if it generically, you can count the number of points in it, and you can at least count it mod 2, which is all we care about, which is why it was kind of nice the prior Seiberg-Witten variant was odd, was 1 in fact. And this I can define to be Seiberg-Witten high zeros. So it's the diffeomorphism, the variant that picks up high 0 for diffeomorphism. It's the V2 coefficient version for Z for the diffeomorphism alpha and the spin structure X. Okay. So some obvious properties of this is the homomorphism, and the proof that it's the homomorphism is you got your data and you pull back, and it's got some number of solutions that you see here if you're doing this for alpha. And if you do another path to data that gives you the amount for beta, and it has some number of solutions, then the data that you get for alpha pullback beta is just a concatenation of these two pieces of data. And so it's just immediately when you put this up, once it's well defined, it's a homomorphism. So this means that, as you probably guessed, we're going to be computing this invariant for the alpha prime, and we can get rid of this stuff. Not big enough lunch, I don't move enough, I'll fall asleep. Comedy of function has happened to other math professors in the past. What? Well, that's 80s, what is it, Gables? Hardly, yes. Q, the cyber-Whitney, I will say of alpha Q prime. This is going to be the cyber-Whitney of EP, R plus, R minus, EP inverse, R plus, R minus inverse. Put in like this. And oh, I need to put in a spin structure. And so the spin structure will be 2p, do a peanut butter spin structure. And so since this is a homomorphism, it's going to be this one minus this one. What? The junction inequality will tell you that this guy has to vanish because this thing is represented by a sphere. I have to be slightly, I probably, I'll do blue plus the junction. And this blue is the wall cross. I'll say a little bit more about that here. Another thing that you can do with this is sort of built on a manifold. Right now, we're thinking of it as the Vx prime plus S2 times S2. But we could get these things off here, changing both family, and making this the 2p plus 1, and maybe it be the same thing without doing the size. Once you do that, I claim that the the pi 0 cyber-Whitney of this reflection is going to be the same as the ordinary cyber-Whitney of manifold without this factor of S2 times S2 in the same spin C structure. And this is the stage where we use the blue plus wall cross, and the picture is when you reflect in the sphere, it takes reflecting in the A plus B sphere, changes the sign of A plus B, but it leaves the other one alone and vice versa. If we do both reflections, it changes the sign of both homology classes. And so in particular, when you're looking at the eta, when you pull back, whatever value eta was here, after we reflect, it comes over here, and there's a reducible, namely where eta is equal to 0, right smack in the middle. And you can solve what happens when you get reducibles. Well, you don't even have to think about this part because Viralia and Kono already did. That's what this wall crossing and Louis formula is. And you don't have to think about this because this is plus and minus 1 by the Morgan-Mark-Casavo paper that I already quoted, which is in particular not a number. And so I'm trying to get an inequality on a genus. I got cyber-Whitney. The junction should come to mind. Viralia proved a really nice one parameter junction formula, which has the usual proof. Right? You take your surface and you blow up enough times to it has non-negative self-intersection, maybe have 0 self-intersection. Its value to the neighborhood is a circle times the surface. And then you do an X stretch, and then you do Gauss-Bonnet using standard cyber-Whitney curvature, scalar curvature estimates. They get an estimate on what the curvature on that surface is, which tells you what the Euler characteristic of the genus is. And so what Viralia's one parameter cyber-Whitney junction says is if the cyber-Whitney pi 0 Z2 of alpha in some class K is not 0. And if J going from sigma into Z is smoothly isotopic to alpha composed J, that implies that the genus, 2 times the genus of sigma minus 2. It's exactly the same formula. It's essentially the same proof. You just have to tweak a little bit because you have to adjust the family when you use an X stretch along an S1 times the family X. Of the self-intersection of the surface plus the intersection of the surface in the Poincare dual to basic class, which in our particular case, if you go back at the very start, we made the class of the surface 2 times D times A1 plus 2D times K times B1 dot. This thing is the peanut butter or double peanut butter 2P times D. B times B is 0, B times A is 1. So this expression is just 4dP, which you notice out one test goes to infinity as P goes to infinity. And so that shows that the genus has to go to infinity. Certainly, the genus is sufficiently small, the examples are different. Finish with 8 minutes spare. That was a theory statement and definition and